Okay, so good afternoon, everyone. So thanks for this opportunity to share my ongoing work that I am currently doing at the Colorado School of Mines. Thank you also to people who are involved in the organization and the logistics of this WISE meeting. Today I'm going to talk about observing and modeling sea-state gradients in the mesoscale down to the sub-mesoscale range. This work is a collaboration with my advisor Bia, Luc Lenin, Nick Pizzo, and I also want to acknowledge people involved in the SWOT mission on the S-mode campaign. Excellent. So as you have seen this morning, in our community, we have recognized that the sea-state is not spatially uniform, especially in the presence of current gradient. You can see the spatial variability of the significant wave height. And as a motivation of this talk, we have good reason to think that because of the spatial variability of the significant wave height, as shown by Bia this morning, we had good reason to think that it might have impact in the upper ocean dynamic or the lower atmosphere dynamic on the near surface wind. This is the motivation of my talk, and also it seems that the spatial variability of the sea state is key for the accuracy of sea surface variable retrieval from space, and this is something that I will discuss at the end of this presentation in the context of SWOT. Okay, so this is kind of reminder from this morning. When you force wave watch with surface current gradient, you can observe spatial variability of the significant wave height. That is the consequence of the presence of current gradient. You have the same snapshot without current forcing on the right. From the different numerical simulation that we have done so far, we have good reason to think that there is a scale dependency between the underlying current gradient and the sea state gradient. So this is something that I try to plot here on the left. So the green colors are the surface current gradient, and the reddish colors are associated with the significant wave height. And you see they match, pretty well. So this is a reminder of the U2H result presented by Bia this morning, for example. Radar altimetry observation have confirmed the spatial variability of the significant wave height, especially when the data have been filtering using the EMD method, as presented by Bia as well this morning. So here on the right, you have 3 wave number spectra. The yellow one is associated with the altimeter data, the black one with the model result interpolated along the altimeter track, force with current, and the same wave number spectra for the simulation without current. Those spectra describe the distribution of the significant wave height variance across the scale. Those are not wave spectrum. So thanks to denoised data, we are able to observe the spatial variability of the significant wave height, but we have some limitation in space. For example, we are limited by the geometry of the footprint of the altimeter. So all the spatial variability of the significant wave height smaller than twice the size of the footprint cannot be observed with altimeter. And this is the aim of this current talk. I want to investigate the sea state gradient at scale unresolved by altimeters. So to overcome this resolution limitation, I have used airborne LiDAR observation from the SIO mass package. So the LiDAR is carried by an aircraft. For people who are not familiar with LiDAR observation, so here on your left, you can see the concept of this LiDAR observation. So this is a simulator that I have developed. The background is a wave field propagating from the left to the right, and the aircraft is scanning above the sea surface and retrieve the sea surface height with a pixel size around 1 meter. And from the variance of the retrieved signal, you can compute the significant wave height (HS) from the variance at the desired resolution. Here you have an example for a segment of 3 kilometers. So from the variance of this SSH, you have one value of the significant wave height. Okay, most of the data that I will present today have been collected during the S-mode campaign, sub-mesoscale ocean dynamic experiment, funded by NASA, and took place offshore the San Francisco Bay between 2021 and 2023. Let's look at data now. So here you have 2 different days of observation. So the background is the significant wave height simulated with WaveWatch 3, and all the dots are one significant wave height computed every 3 kilometers for a day when the sea state was pretty low, and for a stormy day. So let's look at those 2 panels. So on the zoom, here around the airborne LiDAR observation, what you can see first is those dots show discrepancies with the background. First, we see that we have no coherent patterns as we expected from a numerical output, so you can see that doesn't match. And also, the spatial variability from the airborne LiDAR observation seems to occur at shorter scale. So from that result, we were like, okay, perhaps we have some limitation with the current forcing, but the current that we used to force the model were pretty high resolved. So like, okay, perhaps there is something bad with the data. So like, okay, we have a call with Luke. It's like, okay, there is something else with your data. You need to reprocess them. But actually, when we came back to the SSH field, we can't trust Luke's learning data. So here you have two 12-kilometer swaths for the 2 same days. And if you look at the bottom panel, still associated with the stormy day, you can see that along the swath, you have these wave groups, like the waves are organized into groups. And you can see when you compute the significant wave height every 3 kilometers, when you have, for example, here, a strong wave groups organization, we have a stronger HS, because the group, we had good reason to think that the presence of groups increased the variance of the SHS, and subsequently the significant wave height. And this enhancement can reach almost 35% for this example. So the point here is, because airborne LiDAR are resolving individual waves, we have to deal with a new term. So what we can see in the airborne LiDAR observation is a background on unmodulated HS, a fluctuation induced by a potential underlying current, and this new term induced by the presence of groups. And actually, this is something that have been observed in this paper written by Marine De Carlo and a co-author. I recommend you to read this paper. So from SWIM observation, the author have seen that you have a strong spatial variability in the 4.5 Hertz data in SWIM data, in the SWIM box, actually, that are associated with the groups. And there are some strategy to mitigate the effect of the groups from the HS based on the altimeter filter and the spectral shape of the wave spectrum. So, but in this presentation, we won't use this method to look at the wave groups because we want to look at scale definitely smaller, than the size of the box, where the wave groups filtering method have been applied. So the first question that I asked to myself is, what are the spatial scale where the wave groups impact the significant wave height? For that, I switched to a new framework. So I used realistic wave spectrum, and I inverted it, kind of what the Frédéric Nouillet's model does, as presented by Samuel before. So from a realistic wave spectrum, I create a synthetic SSH field, and then I try to reproduce what the airborne LiDAR observe when it scans the SSH. And what you can see here, the colors of the rectangle are associated with the value of the HS computed every 3 kilometers. And we see something kind of similar that we have seen in the airborne LiDAR observation that I was showing to you previously. Just for people who deal with wave groups, to create that kind of wave group field, I only consider linear superposition of waves. Here on the right, sorry for the layout, you have the same experiment as I was showing to you, but for different spectral shape. So the background HS, this HS bar is the same for the 3 experiments. And you can see, according to the spectral shape, the intensity of the spatial variability induced by groups. I repeat, in this synthetic data, there is no current-induced modulation, only groups. So according to the spectral shape, the intensity changed. For narrow-banded and peaked wave spectrum, as shown on the top, you can see you have a stronger spatial variability of HS associated with a group than for simulation performed with a broader wave spectrum. And on the left, I'm showing you the answer of the question, what are the spatial scale where the wave groups impact the significant wave height? So the x-axis is the peakness parameter, which is an indicator of how peaked and narrow is your wave spectrum. And the y-axis is the larger scale where the wave groups impact the significant wave height. So I call this parameter LWG. So the first thing that you can see from this plot is, for small value of QP, here on the left side of the plot, the value of LWG goes up to almost 90 kilometers, which is expected because the wave groupiness is stronger when you have a narrow banded wave spectrum. And you see the opposite for large value of QP. And the second reason from this same figure, and I think this is the main takeaway of this presentation, is when you look at the value associated with the LWG, you can see we are exactly in the same range where the numerical result expected that the main source of variability were from current. So it seems that we have two processes that occur at the same scale, that occur at the same scale and modulate the significant wave height. Now I'm going to talk about how it can impact the numerical result presented by BR this morning. So for that, I did a WaveWatch 3 run with realistic wave current, and I extract the current-induced anomaly of the HS. Then I create an anomaly with the presence of groups from synthetic field. Then I sum those two anomalies, and I get this new map of significant wave height, which is closer to the reality when you take a picture from space. And if you do the spectral analysis of this map, this is what you get. The dashed blue line is the kinetic energy spectrum of the surface current. The solid blue line is the significant wave height wave number spectrum associated with this output. And what you can see is this scale dependency as presented by Bia this morning in the introduction of this talk. Now, when you do the same spectral analysis but with this new field, this is what you get. So you are not colorblind. The spectrum is red, but it's white. So you have this plateau between 30 kilometers and 2 times the pixel size of my simulation. So here what we see is the effect of groups impact the significant wave height at a much larger scale than the scale of the groups themselves. And the variance associated to the groups contaminate or overshadow the effect of current, like in the small mesoscale range. And people, altimeter fans will recognize some feature here that we can see from altimeter output. So I'm not discussing it here, but I would be happy to chat with you about that. So we have two effects that occur at similar spatial scale, wave groups and surface current. Because I'm from current-induced modulation, I wanted to mitigate this effect of the groups with the airborne LiDAR data. So what I did is I considered observation collected during multiple passes. So when the aircraft was scanning the same sea surface throughout a sufficient number of passes, and then I average all the HS together for a given location. The idea behind is to sample the wave groups at different phases. And once you have sufficient number of passes, you should theoretically average the effect of the groups. This is a philosophy, and this is one illustration of this concept. So during that day, the aircraft was scanning the same sea surface 8 times, reciprocal, so yeah, on both ways. And on the right, you have the evolution of the significant wave height. And you can see we have some things that we have seen at the beginning. We have no coherent pattern, sorry. You have sharp gradient between 2 successive observations because of the presence of groups. But once you average all those observations together, this is what you get. So during that day, we had observation for quasi along and quasi across the dominant wave direction. The dominant direction is provided with this white arrow, and I'm going to talk about the across waves observation. What you can see is when you average all those passes together, you still capture spatial variability of the significant wave height at different scale and with intensities that are similar to what is simulated with WaveWatch. On the right, you have some value as a reference. And for example, if you look at this gradient at 10 kilometers, we have an enhancement of the significant wave height by 3% of the background HS, which is comparable with WaveWatch 3 output. And those gradients are definitely not resolved with altimeters. So here we're answering to our first question. Okay, so thank you, the previous group, for the great segue. Now I will talk about the spatial variability of the significant wave height in the context of SWOT measurement. During the IOP2, we had this opportunity to have colocalized mass or airborne LiDAR observation on HS from SWOT, offshore the California current. One dot is one significant wave height from the mass instrument. And the two questions that I asked myself were, should we expect similar HS gradient in the 50-kilometer SWOT swath, on how those gradients can affect the accuracy of the SSH retrieval from SWOT? Here, you have the comparison between the two data sets. On the left, you have all the dots are the significant wave height computed from the airborne LiDAR. On the background is the HS observed by the SWOT satellite. In the middle, you have the delta t between the two acquisitions. So because SWOT is like a snapshot of your HS field, it takes more than 4 hours for the mass instrument to collect the first measurement. Yeah, there is 4 hours difference between the first and the very last measurement in the mass instrument. And in the third column, you have the bias in meter. And this bias oscillates between half a meter when the two platforms have 2 hour difference, but it goes down to 7 centimeters when they sample the same the same part of the ocean at the same time, which confirms the accuracy, for that case at least, the accuracy of SWOT to observe the significant wave height within the 50-kilometer SWOT. And this is the evolution of the standard deviation. I will be happy to chat with you about it, but I prefer to switch. The accuracy of the SSH retrieval from SWOT depends how you correct the effect of the C state, or how you estimate like the estimation of your C state bias. So there's some method, parametrize. So there's some parameterization of the C state bias based on the wind velocity on the HS. And one of the methods that has been used, that is currently used actually in the SWOT data to correct this C state bias, is to compute the C state bias from the nadir HS and then propagate this value across the range. But with that kind of strategy, what happens if you have a special variability of the HS within the 50-kilometer swath? So here, for example, if you use this 3.5 meter to estimate your C-state bias, you will undercorrect your C-state bias at far range, for example, for that measurement. Because here at far range, at 50 kilometers away the nadir, you have a value of 4.5 meter. So because of this special variability of the significant wave height within the 50-kilometer swath, we should expect, or we have good reason to think that the C-state bias will be uncorrected or overcorrected. And this is what I am showing here. On the left, you have the same HS map. In the middle, you have the map of the SSB computed from the HS observed by the SWOT. So the value of the SSB has been provided by Curtis from JPL. And the third panel is the C-state bias anomaly, if you use the nadir observation to correct the C-state bias. And if you look at the bottom right part of the SWOT here, you can see you have an uncorrected SSH because of the C-state bias of the order of 3 centimeters for a scale of 30 kilometers. And that kind of SSH pattern is what SWOT aims to map. So we should expect that, we are expecting that we have some overshadow with this undercorrected C-state bias might lead to overshadowing of SSH feature because of the effect of the C-state. This is my conclusion slide. So we have seen that we have observed spatial variability of the C-state in the meso-to-submesoscale range. We have seen that we have effect of wave groups and current at the same scale, but it's possible to mitigate the effect of the groups to observe the effect of the current by leveraging the temporal scale separation. And this observed C-state gradient might have effect in the accuracy of the SSL retrieval from SWOT. I will be happy to discuss about this last point, especially right after the previous presentation. And I will leave you with this very last sentence. When should we take into account the modulation induced by groups and current in RC processes parametrization? And that's it for me. Thank you very much.